So, Kayla, go ahead.
Well, I chose career theory, and I'm a sophomore in nuclear engineering, so I chose her. It's actually really important in like my career field, and like also really important like women in science. So this one we have like cover her early years. Alright, so she was born in Warsaw on November 7th, 1867, and she was originally known as Maria Sklodowska. Both of her parents were teachers, and she was the youngest of 5 children, 3 of which were girls and 2 were boys. She went to the J. Skidorska School for primary school, but following that, she enrolled in the gymnasium for girls, and she graduated freshman class in 1883, which was also equivalent to getting a gold medal in school. And there's a picture of her when she was younger. So when she was young, her father lost his job, so her families had to take in renters in their small apartments so they could stay afloat financially. And her mother was a devout Catholic, and her dad was an atheist. So she remained like strong in her Catholic faith until her sister died of typhus in 1876. And then 2 years after that, her mother died of tuberculosis, and then after that, she became like agnostic, like lost faith. That's two tragic events. So she knew like after like finishing like her gymnasium school that she wanted to attend university, but since Poland was like controlled by Russia at that time, they weren't girls weren't allowed to go to university, so she couldn't go. So she started teaching at the Flying University, which is basically like an underground university they did at the time in Poland to like help like keep up with the like education system in Poland since like women weren't allowed to go to university. And she made so both her and her older sister, Bronislawa, wanted to go to university, so they made like a pact that like she would help her pay to go to her medical school if she would, once she graduated, help her pay for education. So she ended up taking up various odd jobs in order to help pay for her sister to go to school. So she was a tutor and a governess. And while she was a governess for one of the families in Poland, she felt like the most like intellectually isolated, and she realized she needed to go to university in order to do like what she wanted to do with her life. And she continued to self-educate herself by reading in her spare time when she was not like working as a tutor or governess. And then she also did like a practical scientific training in a chemical laboratory while she was waiting on her sister to finish school. So after that, she enrolled in the Sorbonne University in 1891. And when she was filling out her application, she actually wrote down the name Marie, so she was seeing more French when she went to school. And she quickly realized that like the reading hadn't quite prepared her for university when she got there. So in order to like help her have more time to study, instead of living with her sister when she moved to Paris, she got like a small flat that was close to her school and she would have more study time. So in order to pay for this, she had to tutor at night, so she could like stay like, financially afloat. And then in 1893, she was awarded a master's degree in physics. And then a women's advocate group actually paid for her, like women's advocate education group paid for her to go back and get her master's degree in mathematics, which she was awarded in 1894. And like a picture of a drawing of the Sorbonne University.
She's still there, of course.
Yes. So she realized after finishing both her master's degrees that she was more interested in laboratory work. So she tried to go back to Poland to continue her education, but they still weren't allowed to be women, still weren't allowed to be educated in Poland at that time. So she ended up returning to Paris to pursue her PhD, which is when she ran into Curie Curie, who was an instructor for the School of Physics and Chemistry, and helped her find a better lab space. And this is where I'm going to stop because when it gets into the work like radiance, so I thought that'd be a good topic for big like scientific achievements. I'm really excited.
Things are moving rapidly, of course, in the Manhattan Project, and different sites were being developed. Soon after, as we discussed, soon after General Groves was handed the leadership for the Army, the Manhattan Project, he led the purchase of 59,000 acres near Clinton, near Knoxville. That became Oak Ridge. Also, of course, before that, there was the Met Lab, University of Chicago. This was the first site where Compton, Arthur Compton, the Nobel laureate, Physics was the leader of that. That's where Fermi was. After leaving Columbia, New York City, they went there to build the first pile to demonstrate a chain reaction is possible with a pile of uranium and a pile of graphite. Szilard was there. Many other people were there. But that wasn't the place after Fermi's success with CP1, the first pile of uranium that achieved a chain reaction and ran for 3.5 minutes. That was not the place to build then the first real functioning reactor. That was done at Oak Ridge. So Oak Ridge had dual purpose. Build a reactor, do mass separation of uranium. And we talked about Los Alamos as the second site where Oppenheimer lived and led the laboratory to where you then designed and built the atomic bomb based upon uranium that would come enriched from here. Also in Hanford was started a bigger laboratory for bigger reactors. Fermi demonstrated the principle of a chain reaction in the pile of uranium here. CP1 was built, or the graphite reactor was built here to show you could build a safe, moderated, controllable reactor. Then the production reactors for plutonium were built here, then sending their plutonium produced to here. So those were the sites of the Manhattan Project primarily. We talked about the Clinton Engineer Works. 59,000 acres were purchased in September of 42. A plot of land 17 miles wide by 7 miles, 17 miles long by 7 miles wide. Of course, you got 2 ridges so that you could nestle different aspects of this laboratory safely away from each other. And we had electricity. TVA had been invented. Norris Dam opened in 1936, I believe. So for the first time, there was abundant electricity in the Tennessee Valley. For the first time, there was electricity beyond the cities, primarily. And so this was a good place. Of course, this was there were no paved roads on this reservation. A whole lot of infrastructure had to be built by the Army. A town, schools, paved roads. A new town was created. And of course, it had 3 sites. Y12, that we'll talk about in a moment, where the uranium enrichment facility was by mass separation, electromagnetic separation. The X10 site, which is where the graphite reactor was built, and then the K25 site where uranium enrichment by gaseous diffusion was attempted. So this is really a large effort here in Oak Ridge, by far the biggest. I think it's true of the whole Manhattan Project.
It is 60 cents of every dollar.
Right. And I've shown you this before, but just to recount this, so Ernst Lawrence got the Nobel Prize for the invention of the cyclotron. Cyclotron is a device to accelerate nuclei, charged particles, by using a magnet to bend them in a circle, accelerating them each time to go around, and then increasing the orbit in the circle and producing a elevated energy of a beam of nuclei, of ions. He adapted that cyclotron principle to build a calutron, a California University cyclotron, and was adapted for this purpose, where you had an ion source. Uranium you take out of the ground. It's mostly uranium-238. It's 0.7% uranium-235. Well, that's the isotope you want to have most of, uranium-235. So you start with uranium chloride. You then ionize it. That's what an ion source does. You heat it up. You drive an electron off of the atom, or several electrons, and then you put in a magnetic field. The magnetic field is out of, you got 2 big magnets here. Magnetic field is in this direction. A charged particle then will curve. You know, it's the cross product of the electric and magnetic field, the velocity of the magnetic field. And so it curves, but it curves according to the charge to mass ratio. So they have the same charge, atomic charge on that atom of uranium chloride, but this molecule is a little bit heavier, by 3 out of 200. And so it has a different curvature. So you collect uranium chloride ions here, slightly enriched in mass 238, and here enriched in 235. But that's a slow enrichment process. And Lawrence calculated that he would need 2,000 such tanks, such mass separators with a big magnetic field. And if he had 2,000 tanks, that he would be able to enrich about 3 kilograms over about a year of uranium-235. And this was early on, not 3, but 30 kilograms. That's what you needed was the calculation. For an atomic bomb, you needed 30 kilograms. Yeah, Mark?
Did they try to capture any doubly ionized
I don't know.
chloride?
Is it all just single ionization or? Okay. I mean, doubly ionized would have a larger charge to mass ratio.
So it's curving
Yeah,
inward, so.
right. Yeah, and I don't know.
Using some of the product if they do
They lost most of their products. It went everywhere in there except in that little spot.
Yeah, and I don't know at that temperature, I don't know how much double ionization there was.
Yeah, they probably worked it so it's mostly single
Yeah,
ionized.
probably. So I'll turn it over to Ray to talk more about the Calutron design. Since he is the expert, he spent his career working at Lawrence Clark.
I've done that, and I have seen the Calutrons up close. This particular diagram shows the oval shape, which is where the term racetrack comes from, just because of that oval shape. And I find that when people see this the first time, and I talk about an oval shape and an oval racetrack, they expect the uranium to go around that oval racetrack, which obviously you know that it doesn't do that. The electrical current ties all of these magnets together, and that's what makes the racetrack shape. Now, interestingly enough, these magnets that were in the sharpest part of the bend did not work well. And that's why after the first 3 buildings, Alpha 1, 2, and 3, which had 5 racetracks, 2 in each of Alpha 1 and Alpha 2, and 1 racetrack in Alpha 3, when they decided to double the size of Y12, expanding it, they went to a different design for the alphas, and they made them a rectangular arrangement. But again, the uranium goes in here and comes out at the top, regardless of how the magnets are arranged. So the first 3 buildings had their oval racetracks, the last 2 had rectangular racetracks, and all 4 of the beta buildings were rectangular. So the groundbreaking took place in February of 1943 for the very first building, the Alpha 1, 9201-1. And again, I mentioned to you that although the word uranium was classified, they numbered all of their uranium processing buildings starting with 92, the atomic number for uranium. So you got to know that gave growth a bit. But he didn't say anything about it, just let it go. So that's when they started. And again, the people had to leave that community. New Hope was right where this construction activity is going on now. If you look, you can even see remnants of some of the buildings that are going down. I think that's actually an old chimney. So here's a hint about the oval shape, because that's laying the foundation, knowing that they were going to put something heavy in there in an oval shape. You can begin to get that hint in the shape of the construction and see that there's a good bit of concrete being laid there. If you go down in those buildings today, you can still see, obviously, those columns, huge columns that were built in order to hold the racetrack, which is up on the second floor. So that is the first building, 9201-1, Alpha 1. And notice the configuration, a low bay, what they call a low bay area over here, and a high bay in the center. That high bay in the center is where the Calutrons would be placed. And then the operating controls or cubicles would be off on actually would be on this side, on the south side.
Now, where's the city of Oak Ridge at present? Back here?
No, it's over in this direction. This is Chestnut Ridge. And you're actually looking from the let me hold on to that thought just a minute. Alpha 1, 2. Now the thing that's giving me pause is this steam plant.
Oh.
That steam plant is located, and this turns the whole picture around. I've seen this picture before, and I've seen it inserted in the reverse.
Maybe this has been transposed.
It has, and it's looking really strange too. But if this is accurately set, then Oak Ridge is literally right across that ridge.
Okay.
Because that would be Pine Ridge. But, and it is, and the reason I say that is because of that road. The water treatment plant is right here. That's the gap in Pine Ridge.
Is that where the road goes through?
Mm-hmm.
Okay, to Oak Ridge.
Yeah.
Okay.
So yeah, thanks for letting me pause long enough to look, because that's the direction you're talking about. You're looking south, you're looking north and east.
Yes.
And this is the first Alpha building. right?
First Alpha building, yeah.
And the other Alpha 2 would be back here on the side.
Alpha 1, Alpha 2, and Alpha 3 would be laid in. Oh, that is rich.
You might think I went in and rotate, transpose it just to confuse, right?
Oh, I'm gonna have to study that a long time to figure that
I
out.
was wondering what those two buildings in the back, the smaller ones were.
These,
No, on the right, that you just pointed to,
these,
yeah. Is that 9202?
No.
In the middle?
no, 9202 right here. That would be I believe that's the 9733-1 building. 1, 2, 3, 4 Engineering Road runs right down through there. I think. This is really a good picture.
That looks too tall for it at one of the engineering buildings.
On the first one that you probably never saw, that was torn down very early on,
Oh, okay.
had that, and that's what's making me think that, because 9733-1 had that high bay on the end. The rest of them didn't.
Right.
9731 is right down in there. I think.
Well, I'm proud of myself.
Oh, you got me really thinking, but I think I'm right. So this is the Alpha racetrack, the oval shape with the magnets here, and the Calutrons. The vacuum chambers would have been inserted inside each.
Let's see, how many are in?
There'd be 96 total in one complete racetrack. So there were 5 of those eventually built. And even in the rectangular shapes, they also had that. So this is a control room And this literally is the control room for Beta 1. And the only reason I know that is that's where Gladys Owens worked, and that's the only building she was ever in. So that control room, and it was confirmed by Connie Bolden, who was their supervisor. But that's where the young girls worked, maintained those particular meter readings. And that's what they did every day, was to sit there for 8 hours. Just turn the knob just a little bit, make sure that everything was all right. Now notice these little dots up at the top. Those are red light bulbs. And if the system got out of control, those red light bulbs would turn on. When the red light turned on, the young ladies would back away from the controls, and then some engineering person would have to come and get it back into control, because they only knew to adjust it just a very minor amount. So if anything of significance happened to the setup, it would set off that red light. Also, they were making improvements all throughout the process. As they would make improvements to where they could run, and even Ernest Lawrence came in one time and said, "Is that the best you can do?" And the story is told that he turned the voltage up and turned the temperature up and got a significant more higher level of productivity out of the unit he was working on. So they knew how to increase the production. And remember, they thought they were in a race with Germany, so they were always trying to get more. And as they would do that, what they would do is they would put a shunt across the meter that they had those young ladies watching, so that that meter always went to that spot, regardless of what the actual current was. So they didn't have to train them anymore. They just said, keep it on that spot. And they made adjustments for it to make sure that whatever they changed, they still wanted to keep it on that spot. So they literally had no idea what they were doing. They were just sitting there every day, watching the meter. And when it moved to a certain point, they knew which knobs to adjust to bring it back. Some of those young ladies got good enough at that they would actually know enough about what was being done just by watching those people who were doing the troubleshooting. Although they weren't supposed to do this, one of the ladies told me that she got to where she could actually leave her unit, go out on the tanks and make the same adjustments that she had seen the engineers make, and keep her machine running better than others could do, because they wouldn't go out and make those adjustments. So they did figure out, not knowing what they were doing, but they said, hey, he turned this knob and my meter got back to where it's supposed to be. So when the same thing happened again, you just go out and turn that knob and see if it changes.
Right. How are they evaporating that rainwater to create the gas that's being
That's a plasma. Okay, it's
Yeah.
heated.
You just have a filament,
It's heated.
you know, you have a carbon filament, you run a filament in a chamber.
Right.
And you put in uranium chloride gas at low.
gas?
Heated.
Right.
You heat it up.
It's a low
Actually
pressure
a solution.
solution.
It's a solution,
I see.
because chloride's not a gas.
But it has to then be vaporized.
Yes.
It's vaporized by the heat from the filament, and it drives off electrons depending on the temperature of the filament. And then you have an electric field that extracts that charge. Now, that's where some of the fine tuning comes. You extract, you end up electric field to extract singly ionized or doubly ionized uranium
So
chloride.
there's a little well for each county front?
Yes, there's a little
In there.
pocket that you actually put that feed material in. And the filament he's talking about is just a little D-shaped piece of wire, what it looks like, just a wire.
Like a light bulb.
Yeah, just like a bulb. It's a filament. Only it's about 1/8 of an inch in diameter. And after they're used a while, they become smaller and thinner, and you replace them. But they would stay in there for a long while. And do just what he said, strip an electron off, vaporize it to the point that you had a plasma, one ion at a time being attracted out. like a, I think it's a plus 35 kV anode hanging out there that are cool that,
Now, they're not sitting around the outside of that whole part.
no, they're over in the low bay.
Okay.
They're a good, probably 50 yards away. Well, not 50. Several hundred feet away. Actually, they would be located through a wall. They'd be on a wall, and it would be in parallel with each of the racetracks.
I've seen those. Are they still there, right?
Not these. There are no. The only alpha magnets that are there today is 3 magnets in building 9731 with 2 K.
What are some of those control stations?
The control stations, the Beta 3 control stations in building 9204-3, both sets of them are there. And one of them has never had any modification. It looks identical to this. There's no women and no students. I do have one student. But yeah, it's still there. And Beta 3 is the building that still has the Beta racetrack and the cubicles complete there right now. So the idea was, as you saw that construction getting started, they started installing the Calutrons even before they had completed the building. But unfortunately, the Calutrons didn't work when they first put them in. Is this a good time to talk about that?
Yeah, I think
We
let's
have
talk
something
about
later.
Yeah, here's the problems.
Yeah, the problems that they had, now this happened in 43. Now remember, they started the construction in February of 43. By the summer of 43, they were already putting Calutrons in. Sometime in the summer and the fall, General Groves actually came down to Oak Ridge because of the problem. Problem being that when they started to crank these machines up, they shorted out and wouldn't run. So they actually had to take all of those magnets out of that first racetrack, send them back, because what they found when they opened it up was that the windings, these silver windings, were wound too close, and that they hadn't cleaned the oil sufficiently. So that dirt in the oil caused arcing between the coils, and that was what was shorting it out. So they had to go back, clean them all, and change the spacing between the coils to where that it wouldn't arc over. Now remember, they're running, well, I said there's something like 25 kV. There's some high current going through these magnets, depending on how strong the magnetic field needed to be to make that bend get in the pocket area. And that's what you adjust, change whether the beam goes up here or down here. You want it to hit the top. So you don't change the amount of current flow through the magnet. So that was a major issue. Slowed the process down. I think had influence on can you imagine Groves is sitting here with this Ernest Lawrence assuring him this will work. I mean, he could prove it to him out at Berkeley. He got it going out there. But when they try to scale it up, and the people who are doing these coils, they probably can't even say uranium. They're not scientists. They don't understand. They're building them to a set of specs. And Groves is having that done. At the same time, he's got the graphite reactor also started construction in February. And in June of 43, the K-25 gaseous diffusion plant started. So can you imagine what he's thinking? I don't know if any of these things are going to work. And here, this one has just failed on me completely. And it's the one that Ernest Lawrence says has the highest probability of doing what needs to be done. So he had to be frustrated when he came down here and he said, just tear them out, send them back, redo it, and then come back. And they didn't actually get any uranium produced out of Whitewell until February and March, right over the last day of February, first day of March in 1944. So they'd gone from February of 43 43 to February of 44 and hadn't produced.
So I'll go back here. So if you want to talk to me about that. So
Well, actually, the way, yeah, the alpha K neutrons were very inefficient, and the 10% enrichment is about all you can get out of them. And we haven't mentioned S50. It's always overlooked when we think about these processes, but S50 was built over at the K25 site in late 44 and early 45. And it did the initial separation to get from that 0.7% up to 1, 2, or 3%. That's the toughest part of the whole process, is getting that first little bit of enrichment. Then the K25 became capable of providing more enrichment than 10%, which is about all you could get out of the alphas. So by March of 1945, they were actually feeding material from S50 into K25 into the beta K neutrons, and they were literally skipping the alphas. So those 500 alphas, approximately, or maybe even more than that, were built over in 5 buildings. They had 5 buildings full of them at the time, and they didn't use them when the gaseous diffusion came on. Can you imagine all that silver sunk into it, all of that 5 large buildings? And by the way, Beta 4 didn't actually come online until very late in 45. So they were operating with about 3 buildings, 6 racetracks, 36 K neutrons in each racetrack of the betas. That's what produced the end product of that, about 80% enriched.
this is operated by Eastman, Tennessee Eastman.
Tennessee.
We talked about that the other day. With Sorensen's. Glenn Young is a nuclear physicist who retired from the lab, and he was my student here as an undergraduate in the 70s. And he came, his father worked at Tennessee Eastman. And we just heard the other night that from somebody else that his mother and father probably met here in Oak Ridge. They were probably Tennessee Eastman employees sent down to work on this because there were 4,800 people.
Yeah, they were. And again, by August of 45, you had 22,482 people working at Y12 alone, and that's operations. That's not construction and all that other. That's just that many people operating these K neutrons. And the note here about how it was shipped, again, it was literally put in small gold lined coffee cup size containers, 2 of them in a briefcase, and 2 Army officers would take that material on a passenger train in that briefcase to Chicago. And in Chicago, they would swap, give it to 2 other Army officers who would take it out to Los Alamos. And that's the way they shipped all of the uranium from Y12 out to Los Alamos. So on passenger trains in briefcases. And the shortage of copper, Colonel Nichols actually went to Undersecretary Bell to borrow that large amount of copper. And I'll take this opportunity just to point out something as a historian that is as frustrating as anything you'll ever find. And you have to realize that when you look at primary sources and you try to find specific detailed information, you will tend to find all kinds of variations. The number here is 13,540 tons. I've seen everything from 14,700 tons to all numbers in between. Now, I've actually seen the letters that were written between Tennessee Eastman and the Treasury Department, accounting for the silver as it was turned back in. And they didn't turn it back, all of it, until 1970. They kept 67 tons of the silver in building 9731 in the alpha K neutrons that they used to separate all of the elements in the periodic table. Each year they would send a letter to the Treasury Department saying this process is too important to national security. We can't shut it down. your silver is here in that lot 12 and will be kept for another year. And they did that until 1970. So a frustration that historians have is if you try to use information to gain facts, you must get the primary sources. If you can't get the primary sources, you're likely to see a variation of all kinds of numbers. And that's not intentional on people's part. They do the best they can, they come up with the best, and generally they get close. But it's awfully hard.
Now, what's the
to get
story that
specific.
Grove sent one of his Army guys up to DC to the head of the Mint and said, sir, we want to use 13,000 tons of silver. And what did the guy reply?
He said, oh, you don't understand. Here at the Treasury Department, we don't think of silver in terms of tons. We think of it in terms of Troy ounces. So it was Colonel Nichols who figured on the back of his envelope and said, well, I need about 300 million Troy ounces. And they made a comment in one of the Smithsonian interviews of the scientist Chris Kine, and he and forget the other gentleman's name that was being interviewed, they were asking about the silver. And that's where I learned that they didn't turn it back early on, but they kept it. And Chris Kine said they didn't have to worry about their silver. It was well protected. And he cited the diameter or the density of the steel casing around the coils and the applicator. So he said their silver was safe. So the beta states, again, were the ones that would actually bring the enrichment up to what they call weapons grade and getting up, approaching the 90% uranium-235. And eventually they actually produced enough at Y12, about 60 kilograms, eventually went out to Los Alamos. And that was enough for one little boy and some left over, but not enough for a second. And they did add more racetracks, and the Alpha 2 racetracks that are talked about there are the rectangular ones. They were shaped just like the betas, but you notice the little notch off that makes them look like a D-shaped coil. That's unique to betas. And the fact that the betas were only about 10 feet high, where the alphas were about 20 feet tall, and they had a higher protrusion above them. You see almost no protrusion here. So you can tell the difference in them when you look at them.
When you talk about that.
Yeah. And now we get the gaseous diffusion. You want me to go ahead on that?
Yeah, sure.
So the difference in electromagnetic separation, which was a batch process, and again, 1,152 of those built eventually. The gaseous diffusion process is a continuous operation. You put the uranium hexafluoride gas in at one spot, and then you let it run through what they call cascades. And about 3,000 of those cascades in a building that has a U shape, and it's a half a mile long on each of the legs of the U, with that process running back and forth all the way around. And that continuous operation is what made the efficiency of that process so much better than the Y12 process. 22,000 people to do the Y12 process, about 3,000 to 4,000 operating people to do the K25. Now, the way it works is there's a barrier material that you pump the uranium hexafluoride through, and the holes in a space the size of my thumbnail, there would be 1 billion holes, all the same size, all equally spaced. And that uranium-235 would go through those holes just a little easier, a little faster, because of the difference in the mass than the 238. So you begin to collect or get a little bit more of the 235 in each of the stages. So it began to build up. And the process was a continuous one, and it continued to loop back through itself. It was an amazing maze of activity for that processed material to go from one end up to the other. And it was all pressurized, and it was managed by some 3,000 motors running pumps, huge electrical drain. All of the highly enriched uranium in the nation's weapons today, all that's in the nuclear navy's submarines and carriers, aircraft carriers, all of that comes from the K-25. It operated from 1945 to 1964. And building the barrier was a problem. In fact, they were having so much difficulty with it that they had built the world's largest steam plant to produce some of the electricity for K-25. But because that barrier material wasn't available and ready to work, when Oppenheimer learned about the thermal diffusion process that the Navy was working with, that's when he suggested to Groves, let's build that S-50 plant and using thermal diffusion and build it right beside that steam plant and use the steam from that steam plant to do that. I'm looking at this and saying, you're looking at S-50.
I think I made a mistake.
Yeah, that's not K-25.
That's right.
That's S-50.
Clearly, I made a mistake.
So let's change that K-25 over there and make it a S-50.
Right. So it's just to show where the K-25
Yeah,
site
that's
is.
where, and now the,
And S-50.
see this power plant? That's exactly where the S-50.
Yeah, you said right next.
Yeah, that's S-50 right there, exactly right. And there's the U shape of the K. Now notice on this one, this has the K-25 building, but it also has the K-27 building. In 1945, they went ahead and started K-27. And then later on, in the 50s and 60s, they went ahead and built K-29, K-31, K-33, and then went to Portsmouth and Paducah and built more gaseous diffusion plants up there. So there was a huge operation to enrich uranium that ran from the 45 era up to about 85 before they started shutting K-25 down. And Portsmouth and Paducah ran on up until within the last 5 to 10 years.
Right.
Yes, please.
When I first got to Oak Ridge, I worked at K-25 and I had a lab in the power plant,
Okay,
basement of it.
so you know exactly where that was.
Now, my understanding was to change the speed of the pumps, they actually varied the voltage,
They did.
and they did that at the power
They
plant.
did. That was a variable voltage power plant. One of the unusual characteristics of it was that they were able to do that variation at that power plant. And that was one of the reasons to want to have their own power generating capability.
No, you wouldn't do that because you're putting power on the grid.
Yes,
So here, this is for this very
for this
purpose.
very purpose, you vary it that time.
Interesting.
Okay?
Is that building gone, I assume? Where
No,
he-
it's still
Yeah,
there.
no, it's gone.
Oh, it's gone now,
Power
but
plant
it was there a
It
while.
was there when you were there, yeah. But it was going down probably 15, 20 years. And then there is an image of the K-25 building, half a mile from here to there. They literally rode bicycles inside the building, from one place to the other. It is 4 levels, 4 floors, with the operating floor being on the top and the gaseous diffusion process, a pipe alley, and then a basement area where the pumps and motors and the power.
Yeah,
Talk about
yeah,
the
we can
reaction.
talk about this.
All right.
Right, is there any part of the K-25 building that's still left for future museum?
No, they're gonna build a replica building. That's a good point. I'm glad you asked that. We tried to save the North Tower, and actually, by it being shut down in 1964 and us not really paying attention, roof leak, water got in it, mold, mildew, uranium contamination. Just the cost of maintaining an old building like that, looking to the future, it just didn't turn out to be feasible. So what happened is they now have the footprint of that K-25 building, which is a part of the Manhattan Project National Historical Park. They're building a history center in the second floor of the fire department that's there, right down at the lower end of the open end of the view. And they're also going to build a replica building. Now the replica will be just a slice of the building. It'll be approximately as wide as it was, as tall as it was. And then they'll build some replica condensers and motors and put in there so that you'll have the look of, and we'll be able to see the size. That's the thing you want to impress on people, is how big this building was. So here's the footprint, and then here's a slice of what it looked like. And there'll be a viewing tower at the top of that replica building, so you can see the footprint, and they're going to put some wayside exhibits around the area. So that ought to come in place, a history center next year, and the rest of it probably a year, 2 years later. Thanks for the question. That's an important piece. I have to go make a phone.
All right, thank you. So you can see the uncertainty that we've been discussing. The uncertainty, the uncertainty of not knowing where the Germans started their atomic bomb project before we did. Remember, the U.S. drug their feet for a year until Pearl Harbor. The assumption was the Germans were a year ahead of us. So that's what drove this uncertainty. And then the uncertainty of how to get all the material. You can build an atomic bomb. You had enriched uranium-235, which is what Ray is talking about. Well, that's the purpose of Y12 or K25. This is by electromagnetic separation. Neutrons. But lost time on that because the tanks didn't work. They had to be redesigned. So nothing got produced in 1943, no enriched material. Assumption is the Germans are a year ahead of us. K-25 is gaseous diffusion. That was tough. The barrier business, you need thousands and thousands of sequential separations. That was a tall lift. And so Groves was more focused on plutonium-239 as efficient source as a bomb material, but you had to create that. That's the purpose of a reactor. It doesn't exist in nature. Well, you know, Fermi did CP1 in Chicago. A unshielded, uncooled pile of uranium and graphite. It did go critical. He let it run for 3.5 minutes before he shut it down. He proved that you could multiply neutrons, that the timing was such that it would go critical, have a chain reaction. Well, when that was successful, then CP1, then the idea was to scale it up. Purpose of Oak Ridge, purpose of X10. The next step after that was the graphite reactor at Oak Ridge. And so that's what that was X10. That's now Oak Ridge National Laboratory. So that happened rapidly. But even then, as Oak Ridge being planned, they knew that once that demonstration reactor worked, you need to scale that up even more. This was not meant to be a production reactor. So the step after that would be Hanford, out in the state of Washington. Another desolate place in the middle of nowhere. And that was the idea to a production reactor or reactors would be built at Hanford, Washington. So that site was chosen. Didn't want to do it here, even after graphite reactor worked. Oak Ridge was still too close to Knoxville. If you're trying to scale this up, make production reactors, make kilograms of plutonium, not milligrams or micrograms, worry about having it too close to Knoxville in case an accident occurred. So they went out to Hanford, Washington, off the Columbia River. Columbia River had lots of water. You need water for this process. That was things debated about this production reactor. How are you going to cool it? As I'll show you, the graphite reactor is air cooled. It's a low power reactor. But if you're going to scale this up to make kilograms of plutonium, you need better cooling because you're going to have more power. Well, maybe helium. Helium is a gas. The advantage is it does not absorb neutrons at all. But then you have to get helium up to high enough pressure to give it enough material, enough density to be able to take heat away effectively. And there you need large compressors, and that was a challenge in war-strapped United States. Or you do water cooling. And the fear was that water does, H2O, not heavy water, but normal water, does absorb some neutrons. Would this work? Yeah, you got a lot of water from the Columbia River, but would that really work? Air cooling, like the one at Oak Ridge, thought was that you couldn't carry enough heat away to make enough power. Eugene Wigner, one of the Hungarian Jews that was here in the Manhattan Project, did the recalculation that the water cooling might work, but the K, the multiplication factor, was actually a bit higher, could be a little bit higher than what Fermi had concluded from CP1. And so then at Hanford, water cooling became cooling process of choice. And so that was the design then for Hanford. It was a similar design except for cooling for Oak Ridge. So as they were already planning Hanford, now they were building the reactor at the X10 site to really see if you could build a reactor. And that's what I want to show you in November. This is a national landmark. It's a whole bunch of the hunk of graphite, which is the moderator. And in graphite, you have a whole lot of holes for tubes to go through. And that's where you put the uranium rods, rods that are 3 feet long or 4 feet long or something. You stick them in there. And then you have other slots that are open where you have the air circulating through the very way to generate heat. Of course, you got the graphite matrix that does the slowing of the neutrons. And then after you cook the uranium fuel rod for 100 days or whatever, then you push the rod out and it goes into a swimming pool in the back. You let it sit there and cool off for a month. Then you start to do radiochemistry on it to try to extract the plutonium that you've created. And so that's what I want to show you. That's the face of the graphite reactor. That's still there. Of course, it's been shut down since 1963. And this is a mannequin. There was an elevator here would take you up. You could use these rods to stick a few rods in. And that was designed and then went critical in February. Went critical in November of 1943. The complex started being built in February of 43. DuPont was in charge of the civil construction, and it went very rapidly, of course. There were problems of making that sustained chain reaction go, some problems not understanding the physics of making iodine and that absorbed neutrons and so on. But Wigner came down and helped work out the problems, and then they learned not long after, maybe 6 months after it first went critical, how to keep it critical, how to control it and make it run continuously. You need to know that so you could then scale it up to 3 big reactors at Hanford, Washington. And so, and then the real, I just wanted that, the real, right, so that's the graphite reactor. That building's there. Everything else looks different, but that building's there. It looks older, of course. That's why I want you in the back door to see the face of the graphite reactor. We'll do that in November. And so, but then next to it, under construction, was the building where the radiochemistry was separated, was being developed. How do you take hundreds of kilogram rods of uranium and uranium-238 primarily, and chemically separate out micrograms at most milligrams of created plutonium? A huge radiochemical separation. Well, that's what Mark has done. He's a chemist. But that process was developed here. That was crucial because when you then scale this up, 3 big reactors at Hanford, you have to know how you're going to do the separation of the created plutonium. And that was the contribution Oak Ridge made on the plutonium fabrication, not for production, but for working out how to do it. So Hanford then, after the Oak Ridge reactor went critical in November of 43, people learned how to do the radiochemistry. Then the focus went to Hanford to build 3 bigger reactors, a huge construction job. They decided that water cooling would work, that the dynamics of it, the multiplication neutrons, was a little bit better than Fermi had thought. Wigner figured that out, and that indeed you could do the easier thing of circulating water through there to do the cooling of these bigger reactors. And so that construction went on for 3 250 megawatt reactors, plus facilities, laboratories to extract plutonium. You know, the idea is you have you radiate each rod of uranium material, mostly 238, for 100 days, and you transmute one of those 1 in 4,000 uranium-238 atoms to plutonium-239. That's the level of creation of plutonium that you make. Then you let them, after 100 days of being cooked in this 250 megawatt reactor, you push them out to a pool back of that graphite face, like at Oak Ridge. They sit there for 60 days just to cool off. Some of the short-lived radioactivity dies away, and then gives you a chance to do radiochemistry to extract the plutonium. And that all happened very rapidly. The ground was broken for the first one already in October, before the Oak Ridge reactor went critical. So things were happening rapidly. And you know, it was a big construction project, but you had to build a city too. There was nothing there. So you had, like at Oak Ridge, to move people and create infrastructure for a city, Hanford. Well, there'd be some radioactivity in the water because it's circulating through the reactor. And that was kept in like a storage pool. It wasn't put back in the river. But that's all short-lived radioactivity that you store the water for a while and it's safe to put back in the river. Likewise, in those pools where you put the fuel rods for 60 days, they may pick up, that would be less radioactivity because it's mostly sealed in those aluminum pipes in which the uranium sits. So there wasn't much radioactivity there. But yeah, you're right, you couldn't just dump it back into the river immediately. We know that the Germans were working on their version of atomic bomb. I discussed how the Japanese considered this somewhat. The Soviets also. The Soviets, Igor Kurchatov. There's the Kurchatov Institute now in Russia. Kurchatov was a young nuclear physicist in Russia. And he suspected something was up. He followed the literature through 39 through 42 of people publishing results on this newfound aspect of nuclear fission of uranium. All of a sudden, publications stopped. Those great scientists from the West stopped publishing it, disappeared. He concluded that that was a sign that they were working on using that to make some kind of a weapon, both in the US and in Germany. So he knew something was up. So of course, their effort got set back when the Nazis invaded the Soviet Union in June of 41. His lab that he ran, even at a young age of 36, had to pack everything up and move east out of Moscow because the Germans were knocking on the door of Moscow. So they packed up all their instruments, all their papers, and moved out of Moscow, lost time that way. Of course, they then rebuffed the Nazi initiative, and Germans had to retreat. And then they moved back into Moscow. So it wasn't then until early 43 that the Soviets did establish a uranium program. Sometime after Germany, the US, and England, and they made Kurchatov the director of that. And by a year later, he had assembled 20 good scientists and staff. They built the cyclotron, not in Moscow, but just outside of Moscow. And so that was their version of Los Alamos. But it was all too much, too late, and it never really went very far just because they were late into the game. They didn't really have the resources to work on this very much. I mentioned Leo Szilard. He's also one of the Hungarian Jews that came to be educated in Germany and then came to England and then the US. And he was Fermi's partner in building the first pile, uranium pile that went critical in Chicago in December 42. And he was the crucial guy that went out to see Einstein along with Bohr, and they went back to see Einstein. And he was the guy that actually wrote down the letter that Einstein dictated to President Roosevelt, translated to English, went back and forth with Einstein, and got that letter finished and sent to Roosevelt, alerting the president of the existence of nuclear fission and the threat posed by Germany and the possibility that you might be able to harness that for a huge weapon. So Szilard was crucial in all this from the beginning. He was in Columbia with Fermi. He went to Chicago, part of the PET lab. But he also was in constant trouble with Groves. Szilard was a very idealistic guy who was against secrecy among scientists, against compartmentalization of scientific research. Firmly against that, said he was against military control of the Manhattan Project because they forced secrecy, and that one group of scientists in this part of the lab working on this couldn't talk to this group. So that's not the way science and creativity works. And he was also a rebel. He didn't like authority, much less military authority, especially military authority. And so he was constantly complaining to Groves, General Groves. So Groves put him under surveillance. Thought that Szilard complained so much, is such a pain in the butt, that maybe he's a German spy. And Groves wanted to fire him because maybe he is a German spy. But Arthur Compton, head of the Met Lab in Chicago, although he agreed that Szilard was a pain in the butt, he fought for Szilard and kept him from being fired, although surveillance continued on Szilard throughout World War II. Compton didn't want to fire him because he could lose Szilard, but he didn't want to lose Teller and Wigner and maybe Fermi, who were good friends with Szilard. So Szilard was a malcontent, very smart guy, crucial to the process, but very smart guy. And in his unhappiness, he kept bugging the military during World War II about the patent. it was he already in England, before he came to us, that saw first and wrote down first the idea that if this magical uranium fission emits neutrons, you might be able to have a chain reaction. You might be able to build what we now call a reactor. And when he was discontented with the military here, he fought them hard during the war on, I want to get a patent on this. Well, they said, no, thank you. Can't do that. They wouldn't support him. And that's another reason that Groves had him under surveillance. After the war, Fermi-Enzlar did get a patent on the first idea for a reactor. But during the war, Szilard was always on the edge of being fired or arrested even. Also at this time, desperation was getting higher, worry was getting greater. You know, by the middle of 1943, there was a sense that Germany was not doing so anymore. You know, they got rebuffed by the Soviets. Mussolini got taken out of office. The Battle of Britain didn't work. They had not yet invaded Britain. Hitler intended to invade Britain by mid-1943. Well, that's good that Germany's not doing so well, but the fear is that Germany would do something desperate. And Germany was commonly thought to be a year ahead of the U.S. on developing a weapon. The U.S. by this time, we felt that Manhattan Project felt that they could deliver an atomic bomb by early 45. Well, the Germans are probably a year ahead of us because they got started earlier. So there was worry that by late 43, early 44, the Germans might be so desperate that they might do something crazy like dropping an atomic bomb or at least a dirty radioactive bomb on London. And that drove the Manhattan Project to take some time to think about whether we could use this reactor in a bridge, even before Hanford was built, to make radioactive material, namely the fission products of uranium, which are all radioactive, separate them out chemically, put them in a bomb, not a bomb like an atomic bomb, but just a conventional bomb that you could drop on civilians. And then you might be able to kill 500,000 people that way by dropping a whole bunch of radioactivity on the city. And the fear was the Germans are thinking about that since they are clearly ahead of us to drop such a dirty bomb on London.
How quickly would people die from such a bomb?
Not right away. It wasn't like Hiroshima where you had the big blast, but it would be the people nearest would probably die of radiation damage in weeks or months, and the others would take a longer time. It would be mostly panic. So this was thought about seriously for a little while in the Manhattan Project. Even Oppenheimer, who before he became director was a pacifist and read Sanskrit and the harmony of man, even he thought that this might be necessary to help the dirty bomb. It's a sign of how desperate people were becoming, how the technology kept increasing in World War II. We talked about the discarding precision bombing with area bombing. Yeah, I could take out some military facilities. Mostly you were killing people to discourage the enemy. So luckily in this case, a committee said, no, we're not going to do that in the US, but it was thought about. One final story, I guess I could tell that next time. The heavy water plant in Norway that had been sabotaged once, but the Germans got it running again because they occupied Norway to be making heavy water. It was thought that heavy water was a key part of the German plutonium project. It was assumed the Germans were not going to try to do mass separation, in which Reagan assumed that they weren't heading in this direction. And whereas we decided that graphite would work as a moderator, the Germans had decided that the preferred moderator was heavy water. And thus the importance of the heavy water plant outside of Oslo had been sabotaged once, but Germans had got it working again, and thus, I'll tell you the story next time of how it had to be dealt with once again in late 1943. All right, good to see you.